Alrighty, so the last part of the torsion chapter that we're going to delve into is a little segue into elasticity theory. Probably have time to get through a basic example for this at least. So we'll get started. And what we're going to do here is introduce a topic that gets expanded on in the 4612 class. If you take elasticity or continuum mechanics, the 4612 class, we said that's the one where we get into the X-Men first class and on. We're going to introduce new characters, new formulas, and we're going to make up our own formulas as we go there. Just like all those characters changed actors and they brought in new people and all that sort of stuff. New characters we didn't see before. Sabretooth was that unknown guy and they became Liev Schreiber, right, for the new series. So we're going to be looking at creating our own equations rather than just referring back to familiar. So the first method here we've got is this St. Bernat method that leads us to the Prandtl. And our assumption is we're going to have any arbitrary cross section. All right, so it could be just a blob shape. Constant angle of twist per length. We've been assuming that for everything up to this point, so nothing new there. We are going to allow warping, and it's going to be a function of just the in-plane position warp. So right here, it might warp out of the page, it might warp into the page, might be out of the page here, into the page here. But as a function of the in-plane, and we're going to make X and Y the in-plane, that's just the convention for this method. That means if I go to any slice into or out of the page, I'm going to see the same warping shape. If I go to X equals 2, Y equals 3, and I've warped into the page for this plane, I come out toward you guys 5 feet, I'm still going to get that same warping into the page right here, or anywhere down the length. So that's to say it can have warping, but the warping is going to look the same for every slice we make down the length. Just like before, we've only got non-zero shear stresses and strains. Those are going to be the ones that sit on this plane right here. So sigma xz and sigma yz. We're on the z normal face coming out of the page and stresses that could be going vertically or horizontal. Right, so those are our only two non-zero stresses, and they're only diagonally related on the Hooke's law, so there's only two strains to worry about as well. So basically all the same assumptions we've done before, but this time instead of a familiar or simple cross-section, we can have any cross-section. So we're going to start out with displacements, and we assume there's some angle of twist phi. Right? So this whole cross-section, we said it's all going to twist together, and we want to figure out displacements based on that. Well, the simplest place to go for that is going to be along these axes. Right? If I go anywhere along X and I'm just starting to rotate, my motion along this axis is pretty much all vertical. That's an arc length, but for a tiny, tiny angle, it's pretty much moving straight up. So I can say that based on what I see on the x-axis here, my vertical displacement V is going to be some x distance times tangent theta, or tangent phi. X tan phi is going to give me that vertical displacement based on what I can observe anywhere on this horizontal axis. Right when we start rotating, it's just going to move up or down. And likewise, if I look anywhere along my y-axis, when this initially begins to rotate, I'm going to be moving to the left. So my displacement with a minus sign, since I can see I'm going to the left for a positive angle, negative u over y is also going to be tangent of that angle. So u is going to be minus y tangent. So now I've got an expression. If I know the angle of twist of this face, then I can get the displacements anywhere on there, just as a function of position. All right. And we said warping was also a function of some x and y position. So there's all three of my displacements. I know two of them. I got to just get that warping one later. For a small rotation, we say tangent phi is approximately phi. That's okay. So u is going to be y times phi with a minus sign. V is going to be x times phi. And remember, these are from geometry, this is pretty much an arc length. If phi is in radians, it would be a slightly curved arc length right here, but for a really short angle, it's pretty much the same as a straight line. So that's what we're using to approximate our tangent phi as phi, is that arc length for a short rotation is about the same as this tangent distance. So phi, our angle of twist, is the same all the way across this cross section. So that means this is constant with x and y. It's only going to change when we go further out. It'll have twisted further, go further out in the z direction, it'll twist further. So phi is just a function of z. So that's constant in terms of this xy. All our strains are zero except for xz and yz. And we know to get those engineering strains, we take opposite derivatives. So du dz plus dw dx and dv dz plus dw dy. So if I plug in what I just made for u and I just made for v, go in right there. W, we still don't know, but gamma xc is going to be z derivative of this minus y phi. Well, we said phi only changes with z. Y doesn't change with z. It's its own axis. So that passes through. Y comes out in front, and we get d phi dz. Same story on the right side there. X doesn't vary with z, so x comes out in front, and we got a partial angle partial z. And then our warping is derivatives with x and y in these two. And we can also recognize that that twist per unit length we said was going to be a constant. That's our theta. Before it was d phi dx, now we just got z going this way, but it's still twist per length. So theta goes in, and that's a constant number. So now my strains are going to be gamma xz is going to be minus y times that twist rate plus some warping derivative, and gamma yz is going to be x times the twist rate plus a warping derivative. So stresses, there's only two that are non-zero, and all we got to do is take these strains times g. So there's our stresses, and all these are now in terms of displacement and or position. This is the part I can hear a little bit of snoring going on in the background there, but this is the dry part. We'll get to an illustration in just a couple of slides, so hang in there. Our compatibility condition, just like we had a strain compatibility to make sure that those u and v's going up would match each other, we're going to need a stress compatibility here. I can see dw dx in this stress. I can see dw dy in that one. Well, I do want to know for sure that if I try and integrate up to get w, in both of these cases, I'll get the same thing. All right. So we need some way to tie sigma xc and sigma yz together such that we get to the same derivative of w. So just like in before, where we started taking some opposite derivatives and things like that, we'll do the same thing. I see what it looks like for g times the w derivative on both sides. We solve for that and move everything over. So let's say for sigma xc, I take a ddy on both sides. So I'm going to put ddy for that parentheses, and then partial y passes through the shear modulus, and I get a second derivative w, once with x, once with y. And then on the sigma yz equation, I'll take a partial x on both sides. Well, now I've got the same thing in both equations. Second derivative of the warping, once with x and once with y. So whatever's on the left side of these two must be equal, right? So right here, this stuff is equal to this stuff. So we can set these two equations equal now. And if I move theta, the twist rate, over to one side, it says d sigma xc with y and derivative of yz with x. The difference of those has to equal minus 2g theta. And note, everything on the right's a constant. Twist rate's a constant, g is a constant, and of course 2 is a constant. So this is our relation between those two stresses. Whatever equation we come up with for the stresses has to obey this rule, and that guarantees my warping function comes out the same. Right. So this is a compatibility. It's a stress-based compatibility condition, just like we had strain compatibility. So this is one equation we'll need. One we already got is the stress equilibriums. Remember sigma ij derivative with j plus f sub I equals. So we're going to assume no body force here for our torsional setup, and we've only got two non-zero stresses. So if I write out the three formulas for stress equilibrium, first one I'm going to keep x the same and change the second subscript and the derivative all the way across. Well, the only one that we've got in there that's supposed to be non-zero is sigma xc. Only xc and yz are non-zero. So these two go away, and I'm left with d sigma xc dz is zero. That just says the stress is constant as I come out of the page. Right? No matter which way I go in or out of the page, I get the same xc value. It's only a function of the in-plane position. Well, that's good. We already said that was going to be one of our conditions. Same story with this second one here. The only non-zero one is going to be sigma yz. So chunk these off, and says yz stress doesn't vary with z. So that means every time I take a slice, I see the same stress distribution. It changes going around the xy plane, but it doesn't change in or out of the page. So good enough. And then on the bottom, we finally get one where there's two non-zero stresses. ZZ goes away, but we have ZX and we have ZY. Symmetric, so XZ equals ZX, YZ equals ZY. So that says that the two of these stresses together, d sigma ZX with X and ZY with Y, have got to equal zero. So I got an equation that relates the two stresses to each other. I've got one that relates the two stresses to the twist rate. So there's two equations that we've got to work with. Now, the Prandtl's method is going to say we're going to choose a stress potential function. And you might have heard this capital phi sometimes called an Airy stress function. There's some things like a thick cross-section beam that uses an Airy stress function. In this case, they're going to be a Prandtl stress function. But a stress function is a function we choose, and the derivatives of it are going to give us our stresses. All right. Might be one derivative, might be multiple derivatives down. But that's the definition for a stress potential, is it's some function, we choose it, and we make the derivatives equal to our stresses. It's an in-plane function, so it's going to be the same every time we slice it. That makes sure that our stress distribution doesn't change with z, and we saw that from these two equations. Says we're not supposed to change the stress with z, only with x and y. So we've got to choose this Prandtl function to satisfy our stress equilibrium. That was the last equation we had right here. The sigma xc dx plus yz with y equal to 0. So we've just got to make sure that our Prandtl derivatives obey this rule. And the Prandtl guy chose it so that sigma xc is going to be d Prandtl dy, and sigma yz is going to be minus d Prandtl dx. So if I put those in right here, notice he went opposite derivative as what's already in this equation. All right. So I've got d Prandtl dy in for xc, it gets an x and a y derivative. And if I've got minus d Prandtl dx, and there's already a y derivative here, that means I'm going to get a dx dy on the same function. Right? So for sure, no matter what I pick for this capital phi, this Prandtl function, this equilibrium is always satisfied as long as the stresses come out like this. All right, we all agree there? So now we've got our function and the stresses that are going to come out of it. The only thing we got to do now is choose what this function is. All right. So our compatibility condition says d sigma xc dy plus yz with x subtracted is minus 2g theta. And here was our Prandtl definitions for the stresses. So if I throw those in there, I'm going to get second derivative with y plus second derivative with x equal to this minus 2g theta. All right, so now I got my Prandtl function related to the twist rate. We could also say this is the Laplacian. I believe that's the second del operator, is Laplacian of the Prandtl function. All right, if you think back to vector calculus, all right. And that Laplacian or del squared operator says take second derivative with x plus y plus z. All right. So d squared dx squared plus d squared dy squared. Technically, it's plus d squared dz squared, but we said Prandtl doesn't vary with z, so that would have been 0 in this mathematical expression. So it does equal this right here for a 2D case. Right? And Prandtl's a 2D function, just a function of x. So we can shorthand write it like this. This del squared or Laplacian means second derivative of x plus second derivative. So now we've got twist rate related to phi. We've got the stresses related to phi that satisfy this. Only thing we got to do now is choose it, right? And in the 4000 class, this is what we get into. We've got to choose these functions that satisfy our boundary conditions. The boundary condition we've got for this torsion is a stress-based boundary condition. It says on that free surface, that means if I go along my drive shaft and I take my pen and point it perpendicular out anywhere along that cylindrical surface, we're supposed to have 0 stress. So on that free surface, the outside of the drive shaft or the pipeline or whatever we're looking at, stress has to be 0, 0, 0. And remember our traction vector, we all did that in the test just a couple days ago. Stress tensor dotted with the normal has to equal all zeros for our case, a 0 stress vector. So NX, NY, and NZ. And here's our 2 non-zero stresses that go in here. So the first row of this equation just says sigma xz nz is 0, sigma yz nz is 0 for the second one. Now, these are supposed to be our non-zero stresses. So that just tells you that nz is what has to be 0 in both of these. And if we think about anything with a constant cross section, and that's what our assumption is, I've got z coming this way, say y here, and I've got x here. If I go anywhere down this surface, here's my circumference line around here. That normal vector, no matter where it is on this surface of the cross section, it should never point down the axis one way or the other. If I look at it right here with z, all my surface normals are going to be either coming out of the page or behind it going into the page or down like this. But my surface normal has to be in this XY plane. So those first two ones we don't really have to worry about. That's as long as we got a constant cross section, the surface normal is always going to be in this XY plane. So nothing to worry about there. That's already taken care of. The last one's going to be the interesting one. Sigma xz times the x component plus sigma yz times the y component. And remember, this is a unit vector, has to equal 0. So this is what we've got to satisfy when we pick our Prandtl function. Now we got one more page where we've got to do some geometry, and then we're going to get to where we can pick it. So surface normal, let's just say we zoom in on some lower right to upper left surface. The normal is going to be going positive, positive, nx and ny. And we'll assign just some reference angle beta to that. So that angle beta is there, exactly perpendicular the whole time we go around is our surface direction. All right, normal is always perpendicular to the surface. So surface is going 90 degrees to that. And that means we have a similar triangle. If it's 90 degrees there, our beta is going to show up down at the bottom of this triangle. And that's going to be some x distance and some y distance with a hypotenuse that's the surface direction, ds. And we see if it's positive nx and y, we got a minus or left on the dx and a positive up on the d. So if we consider this all some small distances, cosine of that beta angle is going to be minus dx ds. Sine beta is going to be dy ds. And then on the similar triangle for the surface normal, ny is going to be the hypotenuse cosine beta, but remember it's a unit length, so 1 for the n hat length. And then nx is going to be 1 times the sine beta. So the length of 1 disappears in there, and now we've got our normals as a function of the cosine and sine. And we also have cosine and sine in terms of the surface directions. So we substitute those in there. And now we've got something to plug in for nx and ny that takes us around the path instead of pointing out. So nx was equal to minus dx ds, or ny is minus dx ds, and x was going to be plus dy ds. So if I throw those two in there and change my Prandtl function out here, d phi dy for xz and minus d phi dx for yz, what I've essentially got is some partial derivative. d Prandtl dy ds plus d Prandtl dx ds. Well, that's just a piecewise derivative that says d Prandtl ds equals 0. So here's what we need to pick our Prandtl function. It needs to be a constant value all the way around that surface. Whatever we pick, it needs to hold the value around the surface. So the good news there is, if we can come up with an equation that describes the border or the perimeter or the surface, it's easy to make that equal to a constant. Right? So we just need same value all the way around the perimeter. So phi or Prandtl is going to be constant on S. The easiest constant number that I know of is 0, right? So let's say the simplest solution is going to be to set phi equal to 0 on that surface. So for a circle, I've got x squared plus y squared equals r squared. It's easy to move the r squared over, and now it's equal to 0, right? That we can make into a Prandtl function because it's equal to 0 all the way around the circle. So it's easy to make equations into a root, set them equal to 0, and that's what we'll be doing with our Prandtl function. And then the last thing we got to satisfy is our static equilibrium. Summation of moments equals all of those stresses added up with their torque. And that's the same function we had way back in the chapter 2 slide set. So sigma yz times x minus sigma xz times y gives us our torque about the long axis there. We've got to integrate that with dx dy over the whole area. And then if we think back to the nightmarish differential equations class, we've got to do one of those integration by parts, right? So the d phi dx and the d phi dy come up once, and we get to phi on those, and then times x. This one goes up to phi times y, and then we instead take the, it's like, what is it, u v prime, and then it goes to v u prime minus something, something. I don't remember all of it, but this is how it comes out. All right. Partial integration. This piece goes to here and here. This piece goes to here and here. You guys recall that one ballpark? All right. So the good news is we said that our phi is going to be 0 on the boundaries. So anytime we're at the limits or these extents, now they are changing all the way around, but we got to go from limit to limit. Instead of this being some nasty function of y to get our curved surface limits and all that, we're at the limit, so it's 0. So this goes away, and this goes away. First one and third one out of those 4 terms is gone, because we're setting phi equal to 0 on the boundary. So we catch a lucky break there, and what we're left with is 2 times this area integral of Prandtl. That's going to be equal to our torque. Not unlike the 2 a sub m times q that we got in the thin wall, right? Just 2 times some area integral. So now we've got Prandtl related torque. This is everything that we need to solve for the Prandtl function. The last thing that'll come out as a bonus will be the warping function. Once we've got phi, we can go back and plug it in here, and then we just integrate up to get w. All right. This expression from sigma xc is going to be a dw dx. So we will see everything that's got an x in it. The only thing we might miss is a term that only has y. And likewise over here, the only thing we can miss integrating up with y is a term that only has x. Or constant, but we're going to say there's no rigid displacement. All right, so we're only looking at deflections. So any term that has x and y in it in a single term multiplied together is going to show up here, and it's going to show up here. This one might have some stuff with only X. This one might have some stuff with only Y. So you're gonna take either one of these expressions and then borrow the Y only terms from this one and put them here. Or you're gonna get this expression and borrow the X only terms from this. So we do gotta go up both of them, but we'll see any combined terms have to show up in both places. That's a good sanity check. If we have something with X only, we add it over here. And if we have something with Y only, we add it right. So that's what the G of Y and F of X is. Stuff that we cannot catch when we integrate with X, or here where we integrate with Y. So there's our summary of everything. We choose Crandall to be 0 on the boundary. Then we relate it to G and theta through that compatibility condition. We can find the twist rate with the static equilibrium, that area integral. And then lastly, we go back and get the stresses and. So after the break, we're going to run through this with a circular test case because we know the answer to that one. We know exactly what it ought to look like. We'll see it, how it works, and then we'll try it with a more complicated shape after. So let's come back at 10 minutes after. We'll try the nice easy one with the circle, and then we'll work our way up to that triangular shape. Used to be like $7 a day for that airport long-term parking part. But it's a pretty good deal. So you can park at Millbrae or San Bruno, and then, I think they charge you like maybe $10 to ride over there. But if you're staying more than a couple days, that averages out real fast. I mean, even if you only go for a one-night trip, that's 14 of parking and 10 of BART ride. That's cheaper than one 24-hour period at the economy parking. It's like, that's 25 a day now at SFO. So, and then it drops you right at the terminal too. You walk right off the train and into the terminal. They also don't charge you for weekends if your trip starts or ends on a weekend. Then, like I say, you go Saturday to Wednesday, they only charge you 3 days for that, which is kind of neat. Either Alrighty, so we're back here, 10 after. Let's try a test case here, and all that background that we've just gone through was mainly just to get these couple of equations that we got down here. So we'll try our circular bar first. First thing we gotta do is pick a Prandtl function. Right? And our main rule was that we gotta have Prandtl equals 0 all around the surface. And for a circle, we're in luck because we only have one equation that's needed to describe the whole surface. So Prandtl equals 0 on that surface. And here's our other stuff. Our Laplacian got to equal minus 2g theta. And torque has got to be 2 times the area integral of Prandtl. And if it works out that that we can integrate it with r or something instead of dx dy, that's okay too. So it just is d area. That's an important thing to remember about that one, the dx dy. If we want to go to polar coordinates or something like that, we can do it to make it simple. And then sigma zx is going to be our d Prandtl dy. And sigma dy is going to be our minus d Prandtl dx. I'm just going to write those down before I flip over to the other view. So first thing we got to do is pick our function for Prandtl. We've got a circle here, radius, outside radius of capital R, and it's a solid circle. So let's get on our chalkboard view here. So the equation for this one, pretty simply, x squared plus y squared equals r squared, right? That describes this all the way around the circle, just plain old circular equation, right? If I want to make that equal to 0, I can just say 0 is x squared plus y squared minus r squared. And that's a root equation equal to 0, right? Anytime I'm on the surface, this x squared plus y squared adds up to the radial location, and we're at 0. So my Prandtl function, I want to equal 0. That's got to be something times this. This part guarantees that it's going to be 0 all the way around the surface. And then I need some sort of multiplier because it's probably not going to be exactly this. So we'll put some constant out in front. We'll call that C1. You could call it A, B, C, whatever you like. I like C1, just a constant. And we don't confuse it with anything else. So any constant letter you'd like out in front of here, that's our scaling factor. And then this part, when we multiply it, guarantees that it's 0 on the perimeter. So this one's taken care of now. Next one we got to try out is this Laplacian equal to minus 2g theta. So del squared of this, and remember that's partial x squared plus partial y squared. The z squared is technically in this one, but remember our phi is only a function of x and y. So we just got to take 2x derivatives and 2y derivatives, and then set that equal to minus 2g theta. So let's try our x derivatives first. If I take a derivative with x, I'm going to get 2c1x, and then I take another derivative, I'm just going to get 2c1. So 2c1, that's going to be my x derivative. I got that one. And then here, if I take derivative with y, it's going to be 2c1y, and then one more derivative is just going to be 2c1 again. So there's my 2 second derivatives. Just taking second derivative with x of this and adding it to second derivative of y. Constant down here, so nothing to worry about there for the r squared term. And then we're going to set that equal to minus 2g times theta. So our ratio then is going to be that C1 is going to be minus g theta over 2. Or we could flip that around if we want to say theta. Theta is going to be minus 2c1 over g. One or the other. So now we've got a relationship between that constant. We still need to find it and our twist rate. Then the other one that we've got to work with is this one. Torque equals 2 times our area integral of Prandtl. So let's try that one over here. Torque is going to be 2 times this one, and I'm just gonna set it d area. Right? Instead of dx dy, we'll call that d area. So the Prandtl function, as we have it right now, I can sub in for the C1 with this guy. So my torque can either leave the C1 in there or I can substitute in, go ahead and substitute in theta. We'll go ahead and substitute theta so we can get theta as a function of torque right off the bat. So inside my area integral, I've now got this constant out in front, g theta over 2. And then I've still got this stuff behind it, x squared plus y squared minus r squared, d area. Right. Now, if I want to integrate this with x and y, I'll have to integrate the upper half and the bottom half. I have to say for here, it's going to be y equals square root r squared minus x squared up here. And then on the bottom half, I'd have to say y is minus square root r squared minus x squared. And then I've got to integrate that with dy on the inside. So it would have to be a dy dx. And then I'd have to integrate x from negative r to positive r. This is a horrible thing to have to put up in this definite integral here. We probably definitely agree that we don't want to do that, right? All right, bad joke, but that's on one person's smile, so that's fine. All right, so we want something other than dy dx or dx dy, where we have to take slices like this with these two square root functions in the first integral, and then in the second integral, minus r to r. That's not too bad. But there's got to be a better way, right? Well, the other choice we have is we can do the donut. We already tried that with circular torsion, and we're doing a circle. So let's stick with that. Our other choice, 2 pi r dr. It's dr thick, and it's at some distance, little r out from the middle. So if we do a donut slice, I'm only integrating on one variable, on r. So let's take this out. This doesn't have anything to do. So the 2½ will cancel, and I've got minus g theta out in front. And now let's work up our integral. X squared plus y squared, anywhere in the xy plane is going to be equal to little r squared, right? Some position. If I go some x distance and some y distance, I got a radial distance. That's the hypothesis. So we'll put little r squared here. Big R squared, the border, is a constant. And then my d area is now this donut slice, 2 pi r dr. All right, so that went in for d area right here. And now I've only got to integrate on one thing, r, and that's from 0 to big R. So super easy there, right? No problem. The 2 pi is going to come out in front. So we've got minus 2 pi g and theta all sitting out there in the front. And then inside now, I've got an 0 to big R of r cubed and a minus big R squared little r. That's just dr. So let's bring everything out front. We'll box it and we integrate this one. So it's going to be r to the 4th over 4. And then minus r squared, little r squared over 2. Guys, double check me there. Integrated from 0 to r. Just the two terms, plain old chain rule with r, no terrifying square root expressions to have to work. All right, so let's see what we have come out of here. Minus 2 pi g theta. We plug in at 0, it's all going to go away. So we just do it with capital R. It's going to be big R to the 4th over 4 minus big R also to the 4th over 2. So I got minus R to the 4th over 2 inside the box, or minus R 4th over 4. Thanks for catching that, guys. And then we got minus 2 pi g theta out here. So minuses will cancel out. We get pi r to the 4th g theta over 2. I look about right. All right. So here's my torque now as a function of twist rate. Usually we know what the torque is. We want the twist rate. So let's solve this for theta. I'm gonna get T over here. We'll move the G down. And then let's move all this down here, pi over 2 r to the 4th. Yeah. All right, so pi over 2 r to the 4th, well, that looks an awful lot like the circular J value, right? So there we are. Now we've got T over GJ equals theta based on our Prandtl function. So everything's checking out the way it's supposed to be. So theta now T over GJ. And then we can go back a little bit here, and we said that C1 was going to be minus G theta over 2. So I can go back in here. I've got minus G over 2, and then my theta was T over G, and then that pi over 2 r to the 4th right there. We see there's J intact. I'm going to break that up by getting rid of this 2 and 2 and the G and G here. So constant 1 says it's minus T over pi r to the 4th. So here's my constant. That means I've now got my phi function fully defined. Minus T over pi r to the 4th. And then I've got x squared plus y squared minus r squared. So here's my Prandtl function. I needed two things to get to that function. One, well, besides picking the function and some constant, I did this one, Laplacian equal to minus 2g theta. That relates the Prandtl and the twist rate. And then I relate the torque to the Prandtl with this one. So we've used up both of these. We picked our equation. Now we've done all the hard work. We just get the stresses as a freebie. All we got to do is take the derivatives here. Let's do that real quick. So sigma xz is partial phi partial y, right? There was our definition back here. So if I take that derivative, I've got y squared there. So 2 is going to come out in front. I get minus t times y to the first power. The 2 is going to come out in front. I'll put that right here for a minute. And then over pi r to the 4th. Now, if we move that 2 down to the bottom, minus ty over pi over 2 r to the 4th. So there's J. It made a comeback back here again. All right. So minus t times y over j. Before we've been seeing tr over j, right? So remember, this is just one component. So let's try the yz. And the Prandtl dx with a minus sign is going to give us our yz stress. So that minus is going to cancel out this. I'm going to get t over pi r to the 4th. And then this time I get 2x instead of 2y. So I could say that's t times x over pi over 2 r to the 4th. Again, my j shows up in the bottom there. Now what we're used to is tr over j for the stress. But remember, we said that stress was actually a sigma theta versus axial, a tangential stress that's always going in the tangential direction. Now we've broken that into two pieces, an x and a y piece, wherever we are, right? So these are just components of that tangential stress. If we say sigma theta z, that tau that we normally get for a circular bar is just equal to the sigma yz squared plus sigma xz squared, all right? The hypotenuse is the tau that we're used to. Well, if I do square this, I get y squared, I get x squared plus y squared is r squared. So I get back to tr over j that way. All right. So both of these together, a leg and a leg, does make up the tau that we're familiar with, tr over j, the hypotenuse. Let's just double check on a circle whether these look correct. If I go to some x position out here, x equals r, all right? So over here, I'm at r comma 0. Well, tx over j, I'm going to get a positive sigma yz. So the stress goes up this way, and I'm at y equals 0. So I get no horizontal, which I shouldn't because I'm on a free surface against the horizontal. Let's say I go to the top, I do 0 and R. Nothing doing on the YZ. I don't expect anything that way. And if I put in R up here, I get negative TR over J. That just means it's going to the left, my Y-axis here, my X-axis. If I try it at negative R comma 0, X is at negative R, I'm going down on sigma YZ and nothing on sigma XZ. And then finally, I try 0 comma negative R at the bottom. 0 for this, so no vertical shear, and Y equal to minus R, that cancels this, and my XZ goes this way. So just like a torque going counterclockwise, all my arrows match up with these components here. So the stresses come out just like we thought they should, minus TY over J and TX over J. The very last thing that we got to try is that warping function. So let's take a look at where we are so far with our circular bar. Here's the functions that we came up with. Sigma YZ TX over J, sigma XZ minus TY over J. If we square those up, we do get back to TR over J. And then we need to check the warping. Now, warping is supposed to be 0 for a circular bar. So what we want to do is just go back and try our warping functions right here. All right, there they are. And we've already got our Prandtl stuff set up. So we're ready to go. dWdx is going to be our sigma xz over g minus y theta. And then our dw dy is going to be that sigma yz over g minus x theta. So there's our two functions. We've got theta and we've got sigma already, so we'll just go back and refer on those. And we'll keep some of this stuff in terms of the J's as we go through the warping to make it nice and quick. So let's keep this as is. We want to integrate up to W. So we're going to have to integrate this stuff. We're going to have to integrate this stuff. Sigma xz over g. We had sigma xz as minus ty over j. And sigma yz is tx over j. So sigma xz divided by g, that's going to be this one right here, minus ty over gj. And then on our plus here, we've got y times theta. And if we go back up to theta, here it was, just t over gj, what we're supposed to get for a circle, t over gj, right? Well, I can see pretty quickly right there, this is 0. So if I'm integrating up dx, I can only get a constant. That's a rigid body motion. We're not worried about that. So warping there is going to be 0. I can't see an integral with y only, but we can see it over here. So if we try over here with a dy, let's see what we got. Sigma yz is going to be tx over j, and it's divided by g. And then I got minus x times theta, which is t over gj. Well, there I got tx over gj minus tx over gj. So that one goes away to 0. Warping here is going to be 0 plus anything I can't see with y. Over here, it's 0 plus anything I can't see with x. Nothing with x over here, so this is 0. And nothing with y over here, so this is. So no warping, just like we expect for a circle. So this is about the simplest example we can try. We just needed a nice round function for a circle, set it equal to 0, and everything does come out the way we'd hoped it would. That kind of proves that this Prandtl guy wasn't nuts. Warping came out 0. Our stresses come out like we think, and everything else. So that makes you wonder whether a circular torsion was really come up with the strain and kinematics, or did somebody do this one first? I don't know which one. Chicken and the egg kind of. But they do match up. That's important. So now, did anybody have any questions about the basic steps we gotta check to get through this process? Everybody clear on that one? All right. So we pick Prandtl to be 0. We set this twist rate relation. We plug that back into the torque relation. Now we've got the Prandtl function, and then we go down to get the stresses and then back up. So let's take it up a notch, like George says when he's driving Susan's parents out to the Hamptons. And we're gonna try this one instead. Equilateral triangle. Looks even more fun than the last example we did. Little tougher, but not impossible to do. So let's give this one a try. What we're gonna have to do now is come up with one function for the Prandtl that is going to give us 0 on all 3 surfaces. Now, luckily for us, this is a linear function for each of those 3 lines, right? We can make a line function for each of those. It's a real simple equation. And if we want to make all of them 0 on the same function, we can just multiply those 3 lines together. And then one or the other goes to 0, makes the whole thing. So let's draw out our triangle first. We see it's got heights on the left side there, 2 over root 3 h. H is going to be our horizontal distance. H for horizontal, probably. Whoever thought up this gross example. All right. So H is our horizontal distance. We know for an equilateral triangle, our centroid is at H over 3. And we got 2/3 H the rest of the way. All right. So we know our stresses are 0 at the origin. That's good for torsion as well. So we'll just put our origin right there. We're expecting to get 0 stresses at that spot. We saw at 0, 0, both stresses, they go to 0 on the circle too. And then if we cut that 2 over root 3 for the vertical in half, we get H over root 3 top to middle and H over root 3 middle to bottom. So now it's just a matter of writing out our functions for this one. Let's do the vertical line first because that's probably the easiest. What equation can we write to describe this vertical line on the left here? Close. X, right? Because we're at 1x position, no matter where we are on y. Right? So minus h over 3, you're on the right track. Right? Minus h over 3 equal to x. So this describes our red line right there. Then we've got to get one for the top line. So this is a 2/3, 1/3 kind of thing. I can see right here, this has got to be 2/3 of h over root 3 is where it intercepts. And likewise, this one down here symmetrically is going to be minus 2/3 h over root 3. H over root 3 here, and we go 1/3 of the way down the triangle means this height's going to be right there. So there's my y-intercepts for these two. And then we just need the slope. Well, the rise or fall is h over root 3, and the run is h. So this one's got a slope of minus 1 over root 3, and this one's got a slope of 1 over root 3, right? Here's my run down here, and these are my rise or my fall. So I said this one over this one, the h's cancel, and I get the 1 over root 3, it's going down. Here, this one over this one, it's going up, also 1 over. So I got a slope and a y-intercept. That's pretty much it. My green equation going to be y equal to negative 1 over root 3 x plus that y-intercept over there. Not a happy looking set of numbers, a lot of radicals and such, but it is a linear equation. It's not too bad. Now let's get the third one down here. This time we're going up in slope, so we get 1/√3x minus, for the y-intercept, 2/3 h over. So I got a simple line equation that describes each of these three corners. With the Prandtl function, I've got to be 0 on all three of those, right? So I just need to make sure that all three of those end up at 0. The easiest way to do that is to just multiply them together. So some constant out in front, right? Then we got to do our red one here. All right, we got to make it equal to 0. How about x plus h over 3? That's equal to 0 all the time on the red line. Then we'll throw another one up there. We can do the, let's see, x plus 3. We can do the top one next. We'll do the green one. If I want to keep the x and y on the same side, I'm going to multiply through by that square root 3 just to get a radical out from the bottom. So we'll say it's going to be x plus √3y. And then we got minus 2/3 of h. So everything over to the left side, and then I got rid of the radical in the bottom. So here's my function. You guys can double check. I'm moving the x over here. I'm moving the 2/3 over here. So they switch signs. This one goes to plus, this one goes to minus, and then I got rid of the √3, just multiplied it. When it's 0 on one side, we can do that. Multiply it. And then last part, we got to do that blue one. Again, I'll move stuff over. So I'll move the y over to this side and multiply it through by the √3. So I've got an x minus √3y on that one. And again, a minus 2/3 of h. So there's the function as is factored out. If we want to really go nuts, you want to get nuts? Let's get nuts. Let's FOIL out these trinomials and this binomial. I'll just write that one. So we got x cubed minus 3xy squared. We can hire a middle school kid to do it or get the computer to do it for us. We multiply that through. Here's what we got. Just a polynomial. Biggest order looks like third order with x here and with xy squared. Then we got a couple of second orders and then we got a constant. So it's not too bad. A lot of terms, like terms, end up combining, right? And luckily for us, it looks like the square root stuff magically went away. We had some pluses and minuses that we were able to destroy that stuff. So we're good to go there. Now, our first step, del squared phi equal to minus 2g theta, right? So we got to take a couple of y derivatives, and we got to take a couple of x derivatives to get through there. Let's do our x derivatives first. So I'll do one at a time. Put the C1 out in front. We'll take one x derivative first. So we got 3x squared minus 3y squared minus 2hx. And that's all we got. All right. We still got to take one more derivative, but I'm going to do them one at a time. Then we're going to take one y derivative. So this was d Prandtl dy. Dx. And then we're going to take a first derivative with y. I don't want to take both at once because this is a longer. So now we're taking y derivatives. I got minus 3 minus 6xy to the first minus 2hy there. And then nothing on this guy. And then we'll take the second derivative through here. We got C1. One more x derivative here. That's going to bring me to 6x. That one's going to go away. And I got minus 2h here. And then over here, I take another y derivative. Let's see, I got minus 6x and I've got minus 2h. Well, and this is a good sanity check, I might add. The 6x's are going away. If everything on the left is a constant, then everything on the right better be a constant as well. So I've got C1 and then I've got minus 4h left over here. Anybody do 4H when you're younger, the farm and stuff and original essays, like a scouts kind of thing or FFA? So agriculture, all right. But we're left with 4H, which uses that four-leaf clover for their symbol. So we got that right there, 4H. Minus sign's gonna go away. So we got 2G theta equal to 4H C1. That means we can now list C1 in terms of theta. It's going to be G theta over 2H. Or if we want to flip that around, we could say that theta is also equal to 2 C1H over G. So I got a relationship between that constant and theta. So we're halfway there. Now we got to do that torque sum. I'm not going to recommend that anybody tries that by hand, but we'll set it up and then we'll just find out what the answer is. So the torque sum was 2, and we can't do anything radial components this time. We're out of those tricks to play. So we've got to do either a dx dy or a dy dx type integral. Now, in this case, we do have a function y equals up here, and we have a y equals down here. So if we do the y first and go from those limits, we make a little slice like this, and then we integrate dx from minus h over 3 to h over 2/3 h from here to here. So that's how we'd have to integrate it. Let's just set it up, and then we'll back away and not think about it again. So on the inner ones, we're going to have to take the two y functions, the ones that we originally had back here. So the upper integrand, I guess you'd say, minus 1 over root 3x plus 2/3 h over root 3. And then we go from the bottom to the top. So the blue equation goes in the bottom here. This guy right here for y equals on the bottom. So that's 1 over root 3x minus 2/3 h over 3. And then once this is all in terms of x, the x integral is pretty easy. I go minus h over 3 to 2h over 3. But both of these expressions have all got to be jammed into this x cubed minus 3xy squared minus hx squared minus hy squared plus 4 over 27h dy dx. So I got to integrate this with y, then jam both of these expressions into the y terms, and then I've got to integrate with x and jam these numbers into there. So it's pretty horrific looking at that there. Remember our C1, we do have a substitution for that. We've got, where'd that guy go? Right here, G theta over 2. So we're gonna wave our magic Riemann wand. We get the Riemann sum and the integral and all that good stuff. And let's just bring it down to this. Torque is gonna be 2, the 2 out in front, C1, and then we've got h to the 5th over 15 root 3. So that is to say our constant in terms of torque, 15 root 3 times t. It's not as bad as we thought. It simplified down to just one term over 2h to the 5th. Now I've got the constant. That means b is now fully defined. We've got that one. All right. And then based on our other expression, we said that C1 is also equal to G theta over 2H. So G theta over 2H is also equal to this 15 root 3 torque over 2H to the 5th. That's going to let us solve for theta. H is gonna come up, so now we're down to H to the fourth. The twos are gonna cancel. This one goes to the fourth. Twos can cancel out. What's gonna come down? G will come down. R 15√3, and the torque stays. So now I've got my theta or twist rate given right there. So we've got our twist rate calculated. 15√3 T over GH to the fourth, and then our constant C1. So way back when we started the Prandtl function, this guy right here, I know what C1 is. We'll just leave that in terms of C1 for the time being, because that's a lot of extra stuff to write in. Now we're going to take a look at our stresses. So keep this in our back pocket. We know what C1 is. It's all in terms of stuff we know, H and R. Here's the full polynomial, which is the easy one to take derivatives off of. So let's take some derivatives. Sigma xz is going to be partial Prandtl, partial y. And if we do that one, we're going to get C1, and then we just take, we already took this y derivative before, minus 6xy, and then minus 2h. So I got that sigma xz. My sigma yz minus partial Prandtl partial x going to be C1, and then I got 3x squared minus 3y squared, and what's left over here, minus 2hx. Now remember, our C1 this time was all positive number. If we're doing a counterclockwise torque, and the dimension can't be negative. So our C1's a plus sign. So whatever sign these come out is going to be the way that the stresses point. So we've got our stress values now. The only thing that we need to work to do lastly is to get our warping. So here's our stresses. We got the Prandtl function completely solved. If we peek over here, make sure we did that right. Looks good for our summary. Let's get into the warping shape now. So here's our stresses, and I'll jump back here for a second. Here's our stresses and our warping functions. We said dw dx was going to be sigma xz over g plus y times theta. That's dx. And then warping in terms of y, we're going to say it's sigma yz over g minus x theta. We integrate that up dy. And then plus f. So this time we are going to get some warping. Let's see if we can figure out what that's going to be without taking two. So I've already got my stresses, and then the other thing I'll put up in the picture is we got that theta right there. In fact, if we're going to leave everything as C1, let's write our theta in terms of C1. We found that one back here. It was minus 2 over g times C1. So when we get these thetas in here, maybe we'll just leave everything in terms of C1 for now. So theta minus 2C1 over G. Now, sigma XC over G. So I'm going to have, for this warping function, I'm going to have C1 over G. And then it's going to be minus 6XY minus 2HY plus Y times this theta. This theta was minus 2C1 over G. Look back there. Do I have that as a plus or a minus? Change that. Look back here. Plus. All right. You guys were paying attention, I can see. In fact, I pulled the circle one. So you guys must have been paying good attention. You noticed that. You stopped me. Appreciate that. 2C1H over G. All right, we're gonna move this circle one out of the way so we don't mess it up again. Theta from, here we are from the 4H, right? And heart, health, and something else. I can't remember the fourth. All right, we've got our theta here. All right, so theta 2C1H over G. All right. So if I look here, I got C over G and a minus 2HY, and here I've got a plus 2HY. So this term and this term are going to cancel off. And what I'm left with for the warping is just C1 over G times the negative 6XY. That's integrated dx, and then I have plus anything that I can't see with y. Over here, I got sigma yz over g. So I got C1 over G, and then three terms, 3x squared minus 3y squared minus 2hx. You can probably guess that 2hx should be on its way out. Let's see what we got to work with. And a minus sign in front of everything. You guys are catching it all today. Let's put that one there. And then I've got minus x times theta, 2C1H over G. So there's all my integral stuff. I've got plus C1 2H over G times X minus C1 2H over G over X. So all that can go. And then what we're left with is minus C1 over G and then 3x squared minus 3y squared. That's got to go up with y and then plus any x stuff that I missed. So if we integrate this one, this is an easy integration with x. It'll be minus C1 over G. And we're going up to x squared. So the 6 is going to turn into a 3x squared y. Plus any stuff that's only got y. And then over here, and then over here, I'm going to come up here with y. So I got minus C1 over G. My 3x squared is going to go 3x squared y. And then I've got this guy minus just y cubed, right? The 3 is already in front. That takes care of it for us. Plus some f of x. So the good news, the combined term like we're supposed to get is the same in both places. If I look over here, there's nothing with only x. So this goes away. And then over here, if I look over here, there's a C1 y cubed over G. C1 over G y. So that's my plus on this side. So it's either this, which already has both the terms we need, or this one plus the y. Sometimes you'll get some x only and some y only. This time we only had a y by itself. So let's take a look at the answers now that we've done all that work. Okay. So we got our gy, no f of x, and here's our warping function. Right. If we do some dotted lines across here, usually the interesting thing to think about is where is the warping going to be 0? So I'll do some dotted lines through the center that bisect the edges of the triangle. All right. And along any of those dotted lines that hit one of the corners and go through the center, warping equals 0. That's just how that works out. If we factor it, we can see it's going to be y times y squared minus 3x. Right? So the y, whenever y is 0, that's our horizontal axis. So warping 0 along x-axis, that's the horizontal dotted line. Or it's when y equals plus or minus root 3x. Well, that's perpendicular to the two lines that we defined. We had 1 over root 3 for the top and bottom line. So perpendicular to those goes like that, and that warping is 0 there. And it's pretty awful to pick spots in between those because none of the numbers are nice. But if we just trust what's up here, it alternates in a checkerboard between pluses and minuses for the warping values. I guess you could do the y-intercepts would get you that plus and minus straight up and straight down. Not too bad. X equals 0 on those. But everything else, we've got to do a lot of work. plug in. So if we check on the top, straight up the y-axis, it comes out plus. If we go straight down the y-axis, it comes out negative for the warping. And then everything else kind of checkerboards like that. So this is our warping shape. All right. If we're to look at it, say down the x-axis, we get this kind of a shape on the back edge there. Our Prandtl function shape, actually going to taper to 0 at the corners. I didn't do the best picture, but it's going to be a maximum right at the center here. And what's interesting about that is there's no derivatives when we're sitting right at a maximum in the out of the plane axis. So if there's no derivatives either way, there's no stress, and there's no stress at the center. So this Prandtl function usually domes out and tops up. It should always top out at the centroid. So here's what the shape looks like. Three-legged saddle, alternating up and down. That's what the warping shape looks like. And then our Prandtl function looks something like this, right? We've got a steep shape going up, and it's topped out at 0, 0. And if we look down at the corner, this one shows it best. It actually tapers down to a flat shape where the slopes are also 0. Remember, at the corner, we're supposed to have no stress. At this corner and this corner, this is the one you can see the best. It tapers down to 0. So the one direction we might want to look at, how to do the pen on this one, I think comment, right? This one out of the way so we can draw on there. Edit. Okay, so right here, we have a slope that's going up like this. It's a fairly steep slope, and all of that slope is dx. Right, we got x here, we got y here. Right? So there's no d Prandtl dy at that spot. All right, d Prandtl dy is associated with the xz shear. The d Prandtl dx is at its maximum value, maximum going up right there. So d Prandtl dx is maximum, and negative d Prandtl dx is supposed to be our sigma yz. Sigma yz then is going to be going negative sign, which means our max shear is going this way right here. The yz, all right, it's negative d Prandtl dx. This is the maximum d Prandtl dx slope going straight up this midline here, all right? And that's where we said in our triangle, we're supposed to be the maximum stresses. We're at the middle. Over here, my maximum slope is going up this way. And it just so happens with this Prandtl function, the slope is perpendicular to the net shear stress. So here, my maximum slope's right here. My shear stress is going to go like that. On the back edge, maximum slope's coming up like this, which means the shear is going to be perpendicular to it. Remember those opposite derivatives. So that kind of guarantees that the stress, and the one we can see the easiest is on the back side, the left side here. It's all d Prandtl dx for the slope, and negative d Prandtl dx is tau yz or sigma yz. So that's going down in the negative y direction, counterclockwise around that circle. So we did a pretty complex shape there, but we got to see everything. We got to see the warping shape, we got to see the stresses, and that the stresses made some sense going around. So that's everything that we need to do. The last one that we're going to try in the homework is an ellipse here. It's going to have a diagonal saddle shape and a dome shape, much like the circle did for the Prandtl. So in the last homework problem, we're just going to set up our Prandtl function. Remember, for an ellipse, this is what we got to work with. We can just move that one over, and we've got a root function. And then some useful values along the way. We can see we're going to end up with an x squared dA in the torque equation and a y squared dA in the torque equation. Well, luckily for us, those are moments of inertia. So for an ellipse, something that we know, we can get those moments of inertia. So when you get to the torque equation, y squared dA, just throw in this ixx value. And when we get to x squared dA, we can just throw in this iyy. These are bending moments y squared dA and x squared. All right. And then we'll also, with the one, integral of one dA or negative one dA as it turn out, integral dA is just the area, right? And for an ellipse, area is pi AB. So when you get to the torque equation, these three shortcuts will save you all that horrible square root integration. So just work through that one, just like we did for the circle. It'll go like the circle, one equation, and you just find the stuff, C1 and such as. All right, so you guys have a good weekend and